fractions. So Oleg, over to you.
Okay, so thank you very much. I'm very happy to give a talk at your seminar, and also I'm really pleased to do it while sitting. So it's quite reminds me a bit of COVID times, but nevertheless. Right. So can you maybe mute there yourself? The sound. Anyway, so thank you. So basically, today I'm going to speak about a little bit about continuous fractions and actually the way how you consider them geometrically. So it turns out it's quite important for lattice geometry and the study of triangles, polygons, or whatever. So then also we will make some small links to values of quadratic forms and Markov numbers and something like that, which is also quite a traditional subject of, well, say, modern number theory, and maybe a little bit some excursion to multidimensional continuous fractions. So if, well, it takes a bit more time, then maybe we skip some of the things. So then still, I mean, probably Vitaly can publish the slides just to be observed. Okay, very good, let's go. So here there is some space to advertise my book, Geometry of Continuous Fractions. So it's everything more or less what is in the talk is from there, except of course for the work of 24 with my PhD student. Right, so geometry of continuous fractions. So first of all, what are the continuous fractions themselves? So we start with some two numbers, 7/5, and then we do a kind of Euclidean algorithm. So we subtract 5 from 7, and we get 1 is equal to 2/5. Then we reverse 2/5, and of course everything is the same as it was, but we have this funny writing. Then we have 5/2. We can continue the process in the way it was before. So we extract the floor, which is 2, and then we have 1/2. Basically, we are done here because we have only integers now as an elements, 1, 2, and 2. 1 plus 1/2 plus 1/2. So alternatively, we can say, oh, we can still continue. Let's do the last digit to replace it by n-1 plus 1/1. Yeah, we can do that as well. That's quite important for us. So such expression is called an ordinary continuous fraction, and it is referred to Wallace, maybe it was like 17th century, but of course, this is a byproduct of Euclidean algorithm. So everything what you generate here, the elements A1, A0 to N, they are actually the numbers that you get while using Euclidean algorithm, which you usually forget them. But Wallace was the first who decided that there is something interesting about these numbers as well. And we have the theory of continuous fractions now. For us, it is important that every rational number has a unique odd continuous fraction and unique even continuous fraction. So one of them will end with 1, the other one will end with something which is distinct to 1. That's similar to, well, this example for 7/5. So this is for rational ones, right? For irrational one, it's not here written, but it's just unique. I think we wouldn't have it here in this presentation. That's fine. Okay. So, but this is geometry. As I say, this is geometry of continuous fractions, and therefore you can actually view them from the picture. So alpha itself, original 7/5, we insert as the slope of the line y equals to whatever 7/5 times x, or y equals alpha times x. And then we would like basically to see in the decomposition of our first quarter by this line, we would like to see these numbers. And what we do for that is we take the convex hulls of all integer points that are below this line separately, and the convex hull that are above this line, also convex hull. We build them the boundary.
Oleg, could you remind everyone what the convex hull is?
Oh, convex hull is, I have recently a student who was asking what is the convex hull. And actually I find out that it's quite complicated to explain what is a convex hull. So, I mean, there is a formal definition. If you have, I mean, your set is convex, if 2 points that are inside your set connected by a straight line, I mean, sorry, by segments, which is completely inside that set. So probably now convex hull. Convex hull of a set is the minimal convex set which contains our set. So namely, here we have integer points, but convex hull would be the whole gray stuff below the ray. And we are interested only in the boundary of it. So convex hull can be seen if you take a cabbage and you start to cut, start to cut planes from it, right? So you make a knife and you cut it, and what remains will be the convex hull, yeah? So in 3D, it's like that. In 2D, your cabbage should be like really a two-dimensional dance. Like you make like that, you have a knife, you cut all the stuff. What remains would be the convex set. So like here, we cut everything which is not including our set of integer points over there, right? Below the line. Yeah, so it's in a way biggest, like, I don't know how to say it. Yeah. Okay, did I answer your question?
So if anything remains unclear for our online participants, so please ask.
Yes, I mean, there is another way to see this. Basically, you can say with a long strip, and you put in a single integer point, you put a nail, but not completely, such that it's a little bit outside the surface. And then you go with a strip around it. And basically what your strip will form after you go, after you go from minus infinity to plus infinity, say that will be precisely the convex hull of the set. Yeah. So that's the boundary, the way the string will be there. This is what we like to study. Okay.
Yes. So briefly speaking, the minimal convex set containing the original one.
Yeah. Right. So we have one to the bottom, we have one to the top, right? So how does it look like? So first of all, we start with an infinite ray here, going from minus infinity. I'm sorry, going from whatever, some infinity. Then it is one small segment, then another segment which is larger, and then it's another actually infinite ray as well. So we skip rays, and we are interested entirely in this finite broken line. Only these two elements here and these two elements there. Right, so now we need to introduce some integer invariants. Like in every geometry, so we have invariants of that geometry. So in integer geometry, which will be based on integer affine transformations, I will explain this a bit later. So we have invariants. So the simplest invariant here would be how many points is there inside the segment. So inside this segment, there is no points, therefore its length is 1. Inside this segment, B0, B1, we have 1 point in the middle. So therefore, it splits us to 2 elementary segments. Yeah, so I would like to say that the length is 2. So this segment A1, A2 is much longer, but it contains only 1 point inside, which is integer, right? By that reason, I also call this length to be 2. Okay? Now, as you see, we have this 7/5. If you, so we have already studied before, the continued fraction for it will be 1, 2, and 2. Yeah? 1 plus 1/2 plus 1/2. And it turns out that these numbers, probably I should put colors here. The first one is blue one. The second two is actually red one. And the last two is green one. So if you go alternatively left, right, left, or whatever, bottom, top, bottom, yeah. So then you see this sequence. So for our case, it's very simple. It's 7/5, only 3 numbers, but it can be of length 35 or whatever. Even infinite if you take irrational slope. It will be perfectly describing these best approximations that you see actually SA1, B1, and so forth. They are really the best approximations to approximate the slopes, approximating the slope. Right. So, of course, this picture is very nice.
Or Oleg, could I clarify? So you have the slope 7/5,
right?
Here, so this line starting from the origin, and then essentially you are approximating this, say, complicated slope by using simpler,
in a way, yeah,
simpler straight lines, so with simpler slopes.
Yeah, so that's if you want to approximate. Yeah, so if you want to develop approximation theory, then these vertices of this convex hulls, convex hulls means that you are very close. In general, so if you want to approximate some curve by some polygon, in the convex case, the simplest way is to take just convex hull to consider vertices. So that is done in many different contexts. And that's how the theory is built, actually. Well, I mean, so if you don't have convex set, then you have a problem, of course. Problem, then you need to think how to do that. There are many open problems, by the way, even with this area, when you go to multidimensional cases with like hyperbolic ones or whatever. So then you have different operable, no, not something like hyperboloid ones, right? Anyway, so for now, just I'm saying that this convex hulls actually helps us to see the continual fractions, and indeed, so there is something regarding approximation, but for currently we are interested just in reading the sequence, right? So why it is not quite good? It is not quite good because we have our angle, original angle, like starting from here, going from there, say. But in order to read these numbers, we need actually extra normal. I mean, we need really another axis, which is not usually useful when you do geometry of angles, say. Therefore, it would be nice to read this red 2 from the below sail. And it turns out it's possible to do because broken line has length of edges, but it also has angles here. It turns out that we don't need at all y-axis completely. We just can read number 2 from the angle. So how to define angle? You can define it as area over integer length over integer length. By some reason, if you do like that with integer length, yeah, and area is Euclidean. By some reason, if you define like that your integer sign, and this is really sign rule, there is just 2 is missing here. By some reason, it will be always integer. Yeah.
So like ABC here, is it a triangle?
Yeah, ABC here is any triangle. Yeah.
Any triangle.
Any triangle, yes. So this is the way how I would like to define this integer sign. It's just sign rule. But the theorem is that if you do this definition with integer length at the bottom, then you never have 1/7, but you will always have integer numbers.
Okay, so this notation, so what is it? 1L, L.
So L sign means lattice sign.
Lattice sign.
Or integer sign. L and I, they have the same ratings. Therefore, I prefer to write it with this Li sign, right? It's either integer sign if you do integer geometry, or it's lattice sign because it is an invariant of any lattice, actually.
Okay, so it's, yeah, so it's a complicated sign, but
It's
is
simple.
the length of L of AB, is it the length of AB?
It's integer length of AB. It's number of elementary segments there. This is integer length.
Okay.
So they are over there. So we have discussed them before.
Yeah, okay.
Because otherwise you will have rational numbers. Sorry, you will have numbers below 1. And here you have just integers always. Right. So
and S also an integers, some integer area.
S would be S is Euclidean area.
Euclidean.
But indeed, so in our case for the triangles, it would be integer over 2, I guess.
Okay. When we take vertices,
I think it's quite wrong here. So yeah, so it should be probably twice that. It's like it's integer area indeed. Yeah. Sorry. So like of a triangle, area of a triangle should be just 1. Yeah. Area elementary triangle is 1 for me.
But by elementary mean not containing integer points inside.
Yeah. So basically, I mean, I will give you another definition now, right here. So you take this point, you take vector going down, which is 0, -1, right? And you take vector going this way, but the first one, not the second one, the first way which you meet, which is 2, 3. So, I mean, yeah, okay, anyway, so should I draw it?
If you wish,
does anyone see me? Or
yeah, I think
you see me, yeah?
Yes.
Okay, great. So basically we have here 2 vectors, this way and that way. This vector is 0, -1, and this vector is 2, 3. And basically it is 0, 1, and 2, 3. You take determinant, and you take norm, and this is your integer sign. Right?
So the determinant is
the determinant of these 2 vectors, of elementary vectors in our picture, this is integer side. It's equivalent to integer side.
But it's an alternating sum of the things aside, isn't it? So
Sorry?
the integer
Sorry?
it would end up being an integer, right?
It has to be integer because it's determined, right?
Alternating sum of
Yeah,
the-
there is a bit of a statement to say that this is the same, yeah. But indeed, from here, you see that it's always integer, right? So it's just determined. Right, therefore, it's really very much in use. Okay. So integer side. By the way, so I quite like this thing. So this could be considered as an index again. So integer side is actually index. So you have here two vectors, and so you generate your sublattice using only these two vectors. You can go as much here and as much there. And then if you take index of this sublattice and the whole lattice, then you will have this number. So, but what is actually index? So when you think about index, the simplest is to imagine chess, because in chess you have bishops, right? Whatever. So, and basically you have two bishops, one which is white fielded and one which is dark fielded, right? So this is precisely because you want to cover all the set fields by your bishop. So by one of them you can cover like all these ones, and by another you will cover all the other ones. Yes, this is precisely the definition of actually of this index. Yeah, so this is how many different bishops you need. So then the question for you, if you take a knight, yeah. So if you take a knight, so how many knights do you need in order to cover the whole chessboard? Let's compute. So this way and that way. So this is 2, 1, and 1, 2.
So 3 by 3.
The term, yeah, it's not small, it's in by
Oh.
yeah, it actually, so, and you're allowed to make as much steps as you want, yeah, of course, like here, so you can take any steps. So this is 3. So you need 3 knights to cover the board.
The infinite one.
The infinite one. Why is it so? I thought, I mean, if you play chess, you know that you can put your knight.
Only 2 knights.
Only one knight. You need only one knight to cover everything.
Yeah, you do in chess, right? Yeah.
In chess, yeah. So the point is that here you have another 2 moves which are not explained, I mean, not combinations of these 2, right? You actually, for knights, you have more than 2 motions, yeah? But if you allow knights to do only like that, then you have to make 3 knights on your board.
Right.
So we need new chess.
Yeah.
Chess rules.
It's easier to allow 2 more moves.
Yes. Well, okay. Yeah, but then you need to have your coordinates in order to compute the index, which is more complicated. I like more determinants, actually. I prefer simple net. Anyway, so, right. So here we have this bishop, which can move either downstairs or step 2, 3. And if you can do that, then, well, the index would be 2. You need 2 bishops in order to cover the whole lattice. Right. So, and this is sequence, by the way, this 1, 2, 2 is called LLS sequence, like lattice length sign sequence, right? This is, it's not written. Yeah, okay. So this is just for us to remember. Great. So our next station would be integer geometry. And as I mentioned already, that when you speak about geometry, you basically think about some objects like segments, triangles, angles, polygons, whatever, on one side. And on the other side, you have transformations. So integer lattice preserving affine transformations basically can be understood as just shifts. You just take integer vector and make parallel transportation, or multiplication by matrix with integer entries and with determinant 1. GL means determinant plus minus 1 is also allowed. So just invertible matrices which are with integer coefficients. Right, that's it. So here is a picture of 4 triangles. Can you tell me how many of them are integer congruent?
So integer congruent means
Yes, there is. You can perturb them from there to there. Right. So any guesses?
So we should use probably invariants to distinguish them, right?
Yeah.
So the first two seem to have the same area.
Okay. They're all the same area.
They all did.
Because I mean,
even the same so-called integer area.
right. So I will give you some time when I'm drawing them here. So almost. Right.
The red color is usually
Red, oh, but sounds good, yeah, right? Red one, but this. Let me do red. Oh, okay, nice one. Very nice. So 5 minus one more. So it goes like that. Well, I mean, so to be honest, they are all the same. And probably I will show you just with one pair that they are the same, and then you can basically, because this is the most harder to see that they are the same. So if basically, so this strange transformation basically tells us that you will see them similarly if you just change the basis. So let us pick here bases like that and like that, right? This one, this one. And here I would like to pick bases like that and like that. So you see in this basis, this coordinate will be 0, 1, and this is 0, 2. This is 1, 0, and this is minus 1, 0. So here will be the same, it will be 1, 0. This is 0, 0. This is 0, 1. And twice this vector will be 0, 2. I mean, so, sorry, not available. 0, 2. So it was just 1. And this is minus 1, 0. So you see basically coordinates here and coordinates there are all the same. Thank you, thank you. So this basically implies that the transformation that sends these two vectors to these two vectors is our actual transformation that makes it congruent, right? It's basically just, you see, they have the same integer structure in a way, because in different, it's just the same structure, but in different integer coordinates. Okay.
Say for the first two triangles, is it possible to write down the matrix explicitly? Because people struggle to see what is on the board, maybe because of reflections.
Matrix, okay. So 0, 1. Okay, so right. So basically here, this is 0, 1, and this is 0, 1 there. So 1, 0 should go to 1, 0, and 0, 1, yeah, should go to 1, 1. So therefore, you have this matrix 1, 0, 1, 1, and you need to think either you multiply from the left or from the right. That's absolutely
okay. So for the first two triangles on the slide, the transformation matrix is 1, 0, 1, 1.
Right. So here, by the way, so here it's also easy to see. So 1, 0, 1, 0 goes to 1, right? And 0, 1 goes to minus 1, 0, right? Minus 1, 0. So then, I mean, so it should be 2, 1, minus 1, 0. But again, so it's maybe should be how's it, transposed? That I don't know. I mean, but you understand, yes, basically, this is the way to define the method. Then probably should be transposed. Okay? Because it's matrix of the, yeah, I think it should be transposed.
Should be vertical, yeah.
Okay.
Right.
Transposers of this matrices.
Yeah. But again, so as I see that the point is that you don't need to write this matrices. The point is that you see all the coordinates of the triangles coincide in these different bases. Yeah. If you manage to build this base where coordinates coincide, then they're the same. Because this is like what to say that these two markers are the same. It means that if I take here the coordinate like that, and here coordinate like that, right? So then they will have the same sizes, the same values of coordinates there, right? This is the same as to make this transformation. So basically, I think the simpler is to see really like coordinate left introducing local coordinate there and here. Yeah. But again, so you can think in terms of matrices. Right. Let's go further, right?
Okay, so it was an example for 4 triangles.
It does the same.
But could ask if you will give a more general classification result.
Classification. Yeah, so of course we have, so there is a description and later we will see a bit of classification result.
Okay.
Yes, I mean, the answer is yes, and it is part of this talk. It's a recent result, not recent. So first part going 2008, last part is 2024. Basically, right. So why it is nice for us? Because now we can consider on angles without thinking about any coordinates at all, and we can build LLS sequence just for every angle, every single angle. So here, what we do, we just similarly consider convex hollow fold integer points inside, and of course we have broken line. Like here, we have only two segments. And so for instance, here we can compute integer lengths. The first one will be 1, there is no segments. The second is 2, because there is 1 point inside. And then we can compute the bishop, yeah, the area, the angle. And bishop here is precisely the Chet bishop, because we go 1, 1, or 1 minus 1, determine 2. So therefore we have LLS sequence equal to 1 to 2. That's precisely the sequence for the picture that we have before over here. So this angle is actually integer congruent to this angle.
Like in these two pictures, A and V naught, V0 are the same.
Right. So on the right we have just this broken line, and it is enumerated. Yeah, it is enumerated by by the order from bottom to top. Yeah. So V0, V1, V2 just are the elements of the broken line, starting with A and finishing, ending with B.
Okay, so this integer sign, if I remember correctly, it's the area of the triangle divided by the product of...
Right. It's number of bishops that you need if you want to go, number of bishops you need to cover the plane if you want to go this in that way, is determinant of 1, 1 and 1 minus 1. Yeah. So there are two elementary moves here. This is 1, 1, and this is 1 minus 1, right? And you just take determinant. I think determinant definition is simplest, but you can think of it as an area of this parallelogram, yeah, divided by integer length here, which is 1 integer length there. So it's like area of the elementary parallelogram spanned by this lattice. Okay.
So this angle, do you understand correctly? This angle is simply 90 degrees.
Oh, yeah, right.
Right, 90 degrees. So the integer sign of this 90 degrees is 2.
Right. But on the other integer sign of 90 degree can be 1, right? Because Euclidean geometry has nothing to do with this one. So if you look here, angles are, Euclidean angles are not preserved. Euclidean angles are not invariants here. You can forget about orthogonal stuff at all. It's just your imagination. It's like...
Okay, so Euclidean angles are not invariants, but what are invariants?
Yes. LLS is invariant. LLS sequence is not invariant as a complete invariant of the angle. So basically this sequence 1, 2, 2, this continued fraction, right, is actually a complete invariant, right? So sorry.
Complete invariant of
angles, yeah.
Of one angle.
Well, of angles, yes, of, how to say it, congruence classes of angles, right? So two angles are equivalent if and only if LLS sequences are equivalent. And for every,
not the definition.
This is everywhere. And also every LLS sequence is represented by some angle. So this is what it means complete invariant, yeah. So two angles are the same if and only if their LLS sequences are the same. Firstly, and secondly, for if whatever you write, 1, 2, 3, 4, 5, then I can construct an angle for that.
Uniquely and
uniquely.
How do you call them? integer transformations.
Uniquely up to the integer congruences. So it's like congruence in some word which is coming from Klein studies of geometries. Like every geometry has its congruences, which usually in school sometimes called equivalence, which is not quite true because my two hands are not equivalent, they're different, but they are congruent in Euclidean geometry, right?
Well, not exactly.
Up to that. Okay, so they, I mean, usually potentially they're not equivalent, but they're congruent. So like I don't know, so like whatever. So these two pens, still they're not. I don't know. So these two pens, they are not equivalent but congruent. Anyway, so therefore we have here integer congruence, right?
Invariant, but also they reconstructible, so or realizable.
Oh yes. Oh yes, yes, yes. Yes, yeah, that's what I'm saying. They are realizable actually because of this picture, because you can take any slope 7/5, and for any continued fraction you can build a slope, and for any slope you can build an angle. It's simple reconstructional because of the theory of continued fractions.
But if we're choosing a rational number, then
Irrational number is fine.
Integer.
Yeah, but then your continued fraction will be just infinite.
Yeah.
That's fine.
Process,
Yeah, just I have forgotten to say here probably that you see your continued fraction starts with the h and ends with the h. So this is only for odd continued fractions, right? So like the theory is 1 to 1 to odd sequences, like skip all even ones. So it's A0 to A2n. Yeah. Well, that's how it is. Right. LLS is a complete invariant, and once you have LLS, you can define what's integer tangent. And yeah, so similar to the case here. So here, you remember tangent is just the value of the slope, 7/5. That's basically, well, one of the possible definitions of integer tangent. Let's define for this specific picture of our angle as 7/5, and they will say then the rest are defined by congruence. But alternatively, you can define it here as you build just this LLS sequence using lengths and signs, and then you just, well, write it down, continued fraction, right? 1 plus 1/2 plus 1/2. In this case, that would be your integer tangent. So in our case, integer tangent is 7/5. And we have seen already a notion of integer sign. And that's what I was dreaming in school when I was studying. I was always dreaming, why should I put this complicated roots or something when I can just say that sine is 7 and cosine is 5. So in lattice geometry, it's precisely the realization of my dream, actually, and probably dream of many actual school children, when everything is simple. So integer sign, this bishop stuff, is precisely a numerator of continued fraction. Integer cosine is denominator, and cosine is more mysterious here because there is no simple geometrical understanding of it. Like if you think about sine formula, then definition of sine formula is basically valid here for the sine in integer geometry. But for cosine, cosine formula, I don't know how to generalize it. It's an open problem for many years now. No one knows how to do that.
Oleg, could you clarify the basic concepts again?
Right.
So you are classifying here angles,
right,
denoted by three letters, say A, O, B.
Of course, yeah.
Right.
Yeah.
So the angle BOA, is it the same angle or different?
I mean, it's a very good question, by the way, and the answer is just over there. So can I ask you, angle AOB is the same to angle BOA or not?
Well, yeah, actually, yeah, I don't know.
So I can tell you. So because have a look, LLS sequence here is 1, 2, 2, while for the other angle the sequence will be different, 2, 2, 1. And therefore is different.
So the order is important here.
Yeah, because have a look. This picture, the convex hull, is actually is invariant under transformations. Doesn't matter how you pick coordinates, you will still have one line on the left on the bottom, say, and length 2 on the right, right? So this Vy V2 would be always 2. You can't map V2 to V0 such that this point maps somewhere else, and then somewhere else will map here, but it would not be integer then, right? So just as you see, it's not symmetric. And in this geometry, although it looks like tangents are nearly the same, but the like the stuff that transpose angles are not the same, not always the same, is like astonishing. Yeah. So geometry is very close to the Euclidean one, but very far away from the Euclidean one at the same time.
So there is no somehow a continuous relation between Euclidean geometry and integral geometry.
So I don't know for that. Right. So I don't think continuous, because like have a look here, we have really discrete one like 7, 5, and there it was from 0 to 1. So, but if you go there, like if you go to arctangents, yeah. So these would be arctangents. Arctangents in Euclidean geometry completely coincide with arctangents in integer geometry, like 1 to 1. And here, of course, you have continuous family of them. So like this is very strange, isn't it? Yeah, very unusual. Let's put it like that. So this arctangent gives us, I mean, value of tangent, if you want, gives us actually continuous sequence of angles, comparisons between them in some sense, right? Okay, so let's go back probably. Right. So, well, I mean, the generalizations to broken lines, probably I will go here very quickly and we just go through it, right? So just I would like to say that the question that here we wrote this, you can actually write everything for this boundary of the convex hull, which is in a way convex, yeah? But the question is, if you ask me, okay, I don't want to work with convex stuff, I would like to deal normal, just broken lines, yeah? So like in computer science, it's quite often when you really need some broken line and you would like to have some invariance. So yes, of course, you can do that, but then some of the numbers will be negative. Yeah. So even, well, of course, the point is that here you build, for building continuous fraction, you need an observer, you need the origin somewhere. But once you fix the observer, you can write actually this LLN sequence for every single broken line. And it again, it's written in terms of determinant. So for a k, you take determinant like you start from O A0, O A1, you have this like triangle, then it will be, its determinant will be a corresponding number. And again, so for angles, you have a generalized, say, sine rule here, yeah? We would not use this further, so just I wanted to show this, that there exists a very simple analytical continuation of that geometry to broken lines. Okay?
So we cannot substitute the origin.
Right.
Our lines should be outside.
Our lines should be outside, and even more, actually, lines should not, segments should not have direction towards the origin, yeah, because otherwise you have to divide by 0 somewhere, right? So that's the only condition. So you don't want to divide by 0, right? The determinant will be 0 then, and you don't want to divide by 0. Okay. So the just analytical continuation of that. So with a bit of limitations, again, as you say. And again, we have the name LLS sequence for a broken line. Why not? Yeah, that's a just. I will probably say here we have a similar statement. If we start with orthogonally up, so now we fix basis here, we go precisely vertically, and then we go somehow, and then we write LLS sequence here, which is, I mean, 1, minus 2, 2, minus 3, 5, minus 5 for this, for this particular case. Then we again end up with A3, which will be like here, coordinate minus 2 and 1. Oh, I did it minus 1 over 2, sorry. So that basically that line from O to A3 will have a slope minus 1/2. So this is completely analytically continuous here for every broken line. So therefore, actually, well, I mean, we can skip the first geometric construction, but yeah, okay. But if you want positive ones, then it would be precisely convex hull. Okay, there is some fun when you have broken line, when you have closed broken lines. Then you return back, and then basically your slope is 0. Therefore, here you have 0/1, but for continued fractions, you can actually have 0/1 or 0/2. And these are two different things, because 0/1 means that you return to the same point, but 0/2 means that you return actually to the next one. It's still slope 0, but it's not closed one. So it's precisely should be 0/1. It is counted by continuant of this continuance actually defining whether it's 1 or 2. So I don't want really to go deeper there, but just for you to have this general picture, okay, how the original geometry can be generalized to a more combinatorial settings. Right. So, and that was my paper of 2008, I think. So when I have found this generalization. Right. Now your question, how to describe triangles. So here we are. So here we go. I'm not going really answering this question, but it's nearly the answer to a question, because if you know the angles, you know everything, right? So let us see how it can be done.
Did you mean that 3 angles determine
Right.
the triangle?
Yes, precisely. The question is, which 3 angles can build a single triangle? Yeah, so you have basically triple of angles, and you're asking me, can I build a triangle with them or not? So this is basically our classical, I don't know who actually was doing this, but in the Euclidean case, it is, the answer is like alpha plus beta plus gamma is equal to pi. Yeah. Right, so this is Euclidean analog of this. So what is the classification of triangles? I mean, it's any triple of angles such that alpha plus beta plus gamma is equal to pi. You have unique triangle then up to homotopy, right?
Homothetic.
I don't know how it's called, because in English it's
Uniform scaling.
yes, better. It's much better, because otherwise you have, I mean, you don't understand it's like that or like that. So it's like, yes, uniform scaling, right? So, basically the question is, what would be this formula in lattice geometry? The problem for lattice geometry, the problem for lattice geometry is that you can't actually add, you can add angles, but you can add them in different ways. So, and this is what, I mean, I will have to draw it, because like if you add this angle plus that angle, then you have a straight one, right?
So black marker is good.
It's actually good, so
Yeah,
the one you gave me.
yes.
But also recall that this angle is actually, that we have seen before, is equal to this angle, right? So therefore, this is, in a way, it should be the same as adding this angle plus this angle. But of course, if you add this angle plus another like that, you will have just that one. But these two are not the same, right? So it's quite funny that the way how you add the angles, even the same ones, could be different. So like this is equal to that, this is equal to that, but the addition of them are far away to be the same. So by that reason, really plus is not clear what is plus there. But the good thing is that we can make an ugly modification of our theorem in the Euclidean case, and we can write everything in terms of tangents, right? So have a look. So we can say that alpha plus beta plus gamma is pi if tangent alpha plus beta plus gamma is 0, right? But unfortunately, there are 2 cases here. Then the sum could be either pi or 2 pi. You can construct the whole loop there, right?
So you're assuming angles from 0 to
2 pi, of course.
pi.
Yeah, so therefore you can make 2 pi, and this is not a triangle. And then you have the second ugly condition, that tangent of alpha beta doesn't belong to 0 tangent alpha. This will kill the second condition. So this will kill 2 pi. Okay. Right. So the good thing that this ugly rewriting is completely done in terms of tangents. Yeah. And now we send it to Google Translate, and we just make the theorem in the lattice case, because now everything, we don't have pluses, but we have everything. So basically there exists an English triangle with integer angles alpha, beta, gamma, and here it was conditioned that alpha is acute. Here I don't want to say what is that, but I'm just saying that we can pick one of them, that everything is working, right? Then, so alpha plus beta plus gamma tangent will be actually a huge continuum fraction. Tangent alpha minus 1, tangent beta minus 1, tangent gamma. This tangent is again a huge, is smaller continuum fraction, and this is just would be integer tangent. So let me show an example. So here we have a triangle, alpha, beta, gamma, and as you see, maybe, so if you take the convex hull here, will be just a line going vertically here, therefore we have just one LLS sequence, just 3 and nothing else, yeah, just one H. So this is here 3. For the rest, it's a bit more complicated, but it will be 1, 3, 2, and 1, 1, 1. Right. So in order to check that this triangle do exist, and we know that it does exist, yeah, we do the following: we put first 3, then we put minus 1. Right, 3 minus 1. So then we put our second one, 1, 3, 2, 1, 3, 2, 1, 3, 2. Put minus 1, and then put the last 1, 1, 1 here, right? So we have a long continuum fraction, and if you check it by computer, you will see that actually it's equal to 0. Okay. So the second condition would be like the smaller one. Yes, so it's just 3 minus 1, 1, 3, 2, and we don't want, sorry, to have it to be equal, to be in the segment 0, 3. So 3 is taken from here, right? That's it. So we have two conditions. Therefore, we have checked that this condition is fulfilled, at least for this particular triangle. Okay. So I don't know if this gives you an answer to your question when they do exist. So, but at least we have a formula for it. So this is a complete formula for the triangle with given angles.
For example, if you say sample with 3 angles, alpha, beta,
Right.
gamma, then you can check whether they realize
Yes,
it or
yes,
not.
yes.
However, is it possible to
If and only if.
somehow sample with 100% probability? So you choose a triple of angles.
Oh, yeah.
Always realizable. Is it?
Like how to pick it.
Yeah, how to pick it.
Oh, it's very simple. You first draw a triangle. And then
I love drawing the triangles.
like to guess, yeah. Yeah. Right. So like the question, like if you have, I think to, as far as I understand from the next theorem that I will show, as far as I understand, then actually there is some way to construct having 2 to construct the third one.
For any 2, find
More or less, yeah. I mean, there will be a theorem later. I don't remember how it looks like, but I think it answers your question in this way.
Okay.
Okay. Right. So the question is what to do with n-gons. And basically, okay, so I'll probably remove this. But in order to continue, we need a little bit to go to the curvature theory, and we need to define how actually our broken line bends around one edge. Yeah. So basically, if we have 3 consecutive edges, then there is a very fine invariant. This is length of the middle edge. And then there is one line, which is the closest integer line to this edge. And just I count how many points inside we have on that closest line with respect to the longer line. And that could be considered curvature. Maybe it's better to say it's bending, but not curvature. I don't know. So what would be the best word here? So we fix it as curvature for now because there's a feeling of curvature. So not really, however. So for now it's curvature. It's integer distance of BC minus integer distance B prime C prime. And for just formulas to be nice, we subtract 2 also. Just 2 formulas to make it nice. Right. So then if you add these curvatures, then basically the main theorem is that if you give a sequence of alphas and curvatures, yeah, so then you can do a similar thing for many lines, not 3, but many. So the problem is that before curvatures were always -1. And here, by some reason, you have, I mean, you have option for other ones.
Sorry, curvature of what?
This integer curvature. curvature of sitting in the edge.
Curvature of a straight line segment.
Curvature of a broken line, of course, because straight line will have no curvature, right? So that is curvature of broken line in the edge, but computed with respect to neighboring edges, right? So that's a new notion that we introduced a couple of years ago. And then it turns out then the description of n-gons is precisely given by the sequence of these curvatures and continuous and tangents of angles. Yeah. So if you give me angles and curvatures, then I can check again several conditions. Okay. And then you have it. And as you see, actually the last curvature is described in terms of the rest. So the last curvature is not given. It's basically a formula from the respect of the other ones. So
what's for capital K?
Oh no, so you caught me, so very good. No? I have forgotten that I didn't introduce it. So capital K, okay, so here basically let's go back to this thing, and here you see I built the big continued fraction, right? And it's equal to 0. But actually I'm not interested in the whole continued fractions. I'm interested only in the numerator of it. Yeah, I'm interested if numerator is in 0 or not. And numerator is precisely continuant. So continuant is a polynomial. So if you put, instead of continued fraction, if you put variables a0, a1, a2, and so forth, then you have a rational function. Yeah, something over something. And numerator is the continuant, is a continued polynomial. Okay. Yeah, I should add the slide here. Well, I mean, you know, I don't know.
So this capital K is some polynomial depending on.
Yes, it's polynomial which represents the numerator of the continued fraction.
Okay.
Yeah. So it's basically, I mean, so it's roughly for me, it's the same as continued fraction. Okay, it's the numerator of it. Yeah. So like here, for instance, we have this ratio. That's a bit ratio. It's a bit ratio of two polynomials of two continuous is roughly continued fraction. Let's put like that. And this is only an integer sign, I would say. Yeah, it's better to say integer sign here, right? So continuant would be integer sign in a way.
Can I ask what happens to that last statement when it's 2D? Third bullet point there. Changing sign n minus 3 times is a count, right?
Oh, right. So I have forgotten to say last condition is yes. So basically you have a revolution number. Yeah. And basically you would like to, so this is your broken line. And if you are building polygon, you don't want to have several times passing through it, right? And this is basically, the question is how many times you are allowed to change the sign there, right? You just don't allow to change sign too often or too seldom. Right, let's go further. So this is for K1. And again, we take continued fractions here. We have 4 angles and 4 continued fractions. And we compute the curvatures, -1, -2 here. And yeah, so the first condition would be that this long continued, or if you wish, you can take the whole continued fraction. Then the continued fraction here will have to be 0. Will have to be 0. The second one is for the curvature. The last curvature should be computed then by this formula. And the last condition is like 14 - 1 - 15, 0. So we have this increasing sequence of such things. It changes only one times the sign. Okay, well, so it's 1455, and it's perfectly ended with this first part of my slides, I would say, and I'm very happy about that because I can say that it's basically we can move directly to slide number whatever. So this one. So thank you. No, but I mean, so really, we did quite a substantial part of it, I would say.
Okay. Let us thank Oleg, please. Right. So I hope online participants can still hear us. So please ask questions. So first online participants, because yeah, people in person could ask a bit later. Any questions online?
Should I maybe show some?
Questions on, yeah, if you could show some summary
picture.
or where, say,
Yeah, I mean, so maybe this one.
maybe if you could show the main result from
Main
the
result,
talk
okay,
today.
main result. Main result is development of geometry. So yeah, so this is one of nice results, I would say.
Mhm. So this theorem is a classification theorem.
For me, it's like alpha plus beta plus gamma equals to pi. This is like,
Realizability condition.
right, if you want to say like that. For me, it's generalization of precisely this formula.
Mhm.
It's very not straightforward because you see, so classes generalize in different way. Like for me, again, so you're right. So this can be linked to the classifications. That's a very good point. But still, I would more prefer to think of it as many things in one. Like here we generalize what is plus. Here we generalize what is, I don't know. So how to approach the formula itself
Mhm.
by tangents. Yeah.
Mhm.
So maybe previous slide also here. Yeah. So that's how it started and that's how it evolved.
Okay, so stop the recording.